Hello everyone. In this session, we'll be learning the problems related to the chapter Thermal Properties of Matter. Let us understand the first problem. Calculate the change in volume of an iron block 10 centimeter into 20 centimeter into 5 centimeter if its temperature is raised from 10 degrees Celsius to 40 degrees Celsius. Given that the coefficient of linear expansion of iron equal to 1.2 into 10 power minus 5 per degree Celsius. So here we have an iron block and its dimensions are given as 10 centimeter into 20 centimeter into 5 centimeter. So these are the length, breadth and height. Therefore, volume of that block is known. Now this block is heated from 10 degrees Celsius to 40 degrees Celsius so that there is a change in its volume. There is an increase in its volume. So we need to find what is that increase in volume. First, let us write the given thing. The initial volume of the block V is given as 10 centimeter into 20 centimeter into 5 centimeter. Let us write this in SI units. So 10 centimeter is 10 into 10 power minus 2 meter. 20 centimeter is 20 into 10 power minus 2 meter. And this is 5 into 10 power minus 2 meter. Now multiplying these, you will get 1000 into 10 power minus 6 meter cube. Now volume becomes 10 power minus 3 meter cube. Multiplying these two, you will get 10 power minus 3. Now the change in temperature. The block is heated from 10 degrees Celsius to 40 degrees Celsius. So 40 degrees Celsius is final temperature. 10 degrees Celsius is initial temperature. So T2 minus T1, 40 degrees Celsius minus 10 degrees Celsius. Therefore this will be 30 degrees Celsius. Next, alpha, the coefficient of linear expansion of iron. Alpha is given, which is equal to 1.2 into 10 power minus 5 per degree Celsius. Now let us find the change in volume using this formula. Change in volume is equal to gamma into V into delta T. This gamma is nothing but the coefficient of volume expansion. But we know that the coefficient of volume expansion gamma can be written as 3 times alpha, where alpha is coefficient of linear expansion. Therefore, substitute this gamma by 3 alpha. What we get is delta V is equal to 3 alpha V into delta T. Now we know all these values, therefore substitute them. 3 is written as it is, alpha is 1.2 into 10 power minus 5, V is 10 power minus 3, delta T, change in temperature is 30. So multiply these things, you will get 108 into 10 power minus 8 meter cube, and if you write this in a decimal form, you will get delta V equal to 1.08 into 10 power minus 6 meter cube. Well, we'll move on to the next problem. When 0.15 kg of ice at 0 degrees Celsius is mixed with 0.3 kg of water at 50 degrees Celsius in a container, the resulting temperature is 6.7 degrees Celsius. Calculate the latent heat of fusion of ice. And they have given that the specific heat of water, SW refers to specific heat of water. Specific heat of water is 4186 joule per kg per Kelvin. Now, in this problem, we have two substances, ice at 0 degrees Celsius and water at 50 degrees Celsius. So, comparing these two, ice at 0 degrees Celsius is cold substance, water at 50 degrees Celsius is hot substance. So, when they mix together, what happens is ice gains the heat energy and water lost the heat energy. So, according to the principle of calorimetry, the heat gained by the ice will be equal to the heat lost by the water. Therefore, by equating them, we can obtain the value of latent heat. First, let us write the given things here. For ice, the mass is given as 0.15 kg and temperature is, initial temperature of the ice is 0 degrees Celsius. Next, for water, mass is 0.3 kg and its temperature is 50 degrees Celsius. And also they have given the specific heat of water. This is 4186. Now, when they mix together, they comes to the common temperature after exchanging the heat energy. So, the common temperature after exchanging the heat energy, that will be T, that is equal to 6.7 degrees Celsius. Now, first let us write heat gained by the ice. So how much of heat is gained by the ice? Ice is initially at 0 degrees Celsius and finally it has to come to the 6.7 degrees Celsius water. Therefore, heat gained by the ice, that can be written as M1LF plus M1SW into T minus T1. This M1LF is nothing but the quantity of heat energy absorbed to change its state from ice to water. So at the same temperature 0 degrees Celsius, the change of state occurs from ice to water. So that is written as M1 into LF. Plus, now the 0 degree Celsius water, that has to be converted into 6.7 degrees Celsius. So for that, the heat energy absorbed is this M1SW into T minus T1. Therefore, by absorbing this one and this one, this much of energy, the ice is converting into 6.7 degrees Celsius water. Therefore, let us substitute the values here. M1 is 0.15, LF is written as it is. This has to be calculated. M1 is again 0.15. Specific heat of water is 4186 into T minus T1. The common temperature is 6.7. Initially, ice is at 0 degrees Celsius. So this is 0. Now, heat gained by the ice. 0.15 is common here. So take this 0.15 outside. LF remains here. So LF plus multiply this and this, you will get this one. So this much of heat energy is the heat gained by the ice. Next, let us write the heat lost by water. Heat lost by water is M2SW into T2 minus T1. Let us substitute them. M2 is 0.3 and specific heat of water is again 4186. T2 is the final initial temperature of the water, which is 50 degrees Celsius, and common temperature after mixing is 6.7, so 50 minus 6.7. Now the heat lost by water, after multiplying these, you will get this much, 54,376.14 joule. Now by the principle of calorimetry, heat gained is equal to heat lost. Therefore, let us equate them. So heat gained is written in the previous slide, which is equal to 0.15 LF plus 28,046.2. This will be equal to heat lost, which is written here. Therefore, this is 54,376.14. Now we need this LF. So take this 0.15 to the denominator and take this term to the right hand side. So we get LF is equal to this minus of this. And when you divide this, you will get this much. And this is written as it is. After subtracting these two, you will get 334461.4. Now if you write this with an exponential, so LF, that can be written as 3.34. So take this decimal point towards the left side by 5 digits. So 3.34 into 10 power 5 joule per kg. So this is the latent heat of fusion of ice. Now we'll move on to the next problem. So in this problem, calculate the heat energy required to convert 2 kg of ice at minus 20 degrees Celsius, which is kept in a calorimeter, to water at 20 degrees Celsius. Now they have given the specific heat capacity of ice, specific heat capacity of water, and also the latent heat of fusion of ice as this much. Now this problem can be understood with the help of a block diagram. Initially, the ice is at minus 20 degrees Celsius, and by absorbing this much of energy, ice is converting into 0 degrees Celsius ice. So minus 20 degrees Celsius of ice is converted into 0 degrees Celsius of ice by absorbing this much of heat energy, because we need to convert from minus 20 to plus 20 degrees Celsius water. So in this process, first we need to convert minus 20 degrees Celsius of ice into 0 degrees Celsius of ice. So this is the heat energy absorbed. Next, this 0 degrees Celsius of ice have to be converted into 0 degrees Celsius of water. The next process or the next step is ice is converting into water. So this occurs at the same temperature by absorbing this much of heat energy, M into LF. This is nothing but a latent heat of fusion, correct? So by absorbing this much of energy, the ice is converting from 0 degree Celsius of ice into 0 degree Celsius of water. Next, we need to convert 0 degree Celsius of water into plus 20 degree Celsius. Now for this step, Q3 is equal to M into SW into delta T. So this much of heat is required to convert 0 degree Celsius of water into 20 degree Celsius of water. Therefore, for converting ice which is at minus 20 degrees Celsius into water at 20 degrees Celsius, these are the steps involved. First, this is converted into 0 degrees Celsius ice by absorbing this energy. 0 degrees Celsius ice is converting into 0 degrees Celsius water by absorbing this much amount of energy. Next, 0 degrees Celsius water is converting into 20 degrees Celsius of water by absorbing this energy. Therefore, the total energy required can be written as this Q1 plus Q2 plus Q3. So that is what written here. Q is equal to Q1 plus Q2 plus Q3. And Q1 is equal to this M into SI into delta T, where SI is specific heat of ice. And Q2 is this M into LF, where LF is the latent heat of fusion of ice. Then Q3 is this M into SW into delta T. This is specific heat of water. Let us substitute the things. All the things are given here. Mass is 2 kg, SI is this, delta T, the change in temperature in this step is from minus 20 to 0, means 0 is the final temperature, minus 20 is initial temperature, therefore 0 minus of minus 20 plus latent heat of fusion and mass, they are substituted as it is, plus mass is again 2, SW, the specific heat of water is 4200, and final temperature, the change in temperature of water from 0 to 20, 20 is final temperature, 0 is initial temperature, therefore 20 minus of 0. Now let us multiply these things. So we'll get 84,000 in the first term, and this is in the second term, and this is the third term. And adding these, you will get 922,000 joule, or if you write this in an exponent form, Q is equal to 9.2 into 10 power 5 joules. So we have written in a decimal form as 9.2 into 10 power 5 joules. Well, we'll move on to the next problem now. A liquid cools from 60 degrees Celsius to 40 degrees Celsius in 10 minutes. What is the temperature of the liquid in next 10 minutes? So given that the temperature of the surroundings is 5 degrees Celsius. So here we have two cases. In the first case, the liquid is cooling from 60 degrees Celsius to 40 degrees Celsius. The time taken for this process is 10 minutes. In the next 10 minutes, the liquid is cooling from 40 degrees Celsius to some value. So we need to find out what is the temperature after from this 40 degrees Celsius to next temperature. Find it in 10 minutes. They have given it 10 minutes. See, in the first case, let us write the initial temperature. The liquid is now cooling from 60 to 40. So initial temperature is 60 degrees Celsius. Final temperature is 40 degrees Celsius, and the surroundings temperature is constant, which is equal to 5 degrees Celsius, and time taken for cooling from here to here is 10 minutes. Now by using the Newton's law of cooling, we write this equation: T1 minus T2 by T is equal to K into T1 plus T2 by 2 minus of T naught. Now T1 minus T2 is this 60 minus 40, which is equal to 20, divided by time taken is 10 minutes. So substitute the T as 10 minutes only. This is equal to, this is a constant K, and this constant K is written as it is, T1 plus T2 by 2. So 60 plus 40 by 2 minus of surroundings temperature is 5. So this gives us, if you multiply this, multiply and divide it and subtract it, you will get 45. So K into 45. Here we have 20 by 10, 20 by 10 is 2, so 2 is equal to 45K, or this constant K is equal to 2 by 45. So take this as equation number 1. Now the second case, in the second case, what is happening? The liquid is now cooling in next 10 minutes. So for the next 10 minutes, what is the fall in temperature from 40 degrees Celsius to next one? So initial initially the temperature is 40 degrees Celsius, and for 10 minutes what is the fall in temperature. So this is need to be calculated. And surroundings temperature remains constant, that is 55 degrees Celsius only. Now using the same equation from Newton's law of cooling, T1 minus T2 by T is equal to K into T1 plus T2 by T 2 minus of T naught, and substitute the things. T1 is 40 now, T2 has to be calculated, it is written as it is, and time taken is again 10 minutes, so write this as 10 here. This is equal to, this constant is already written, K is equal to 2 by 45 from equation number 1. So 2 by 45, and this is 40 plus T2 by 2 minus of 5. Now if you substitute for T2 and finally if you calculate the values, you will have this step, 40 minus T2 by 10 is equal to 30 plus T2 by 5, and you can find the value of T2 as 27.27 degrees Celsius. Fine. Now we'll move on to the next problem and the last problem. And the two stars radiate maximum energy at wavelength 3.6 into 10 power minus 7 meter and 4.8 into 10 power minus 7 meter respectively. What is the ratio of their temperatures? So we know that any hot substance will radiate the energy, and they have given the wavelengths of those radiations. The first star is emitting the radiation of wavelength lambda is equal to 3.6 into 10 power minus 7 meter, and the second star which is emitting the radiation of wavelength lambda m2 is equal to 4.8 into 10 power minus 7 meter. Now according to Wien's displacement law, we know that the product of this wavelength and temperature, absolute temperature, so this is equal to constant. So by using this convention, for those two stars, lambda into T1 is equal to lambda 2 into T2. So lambda 1 into T1 is equal to lambda 2 into T2. So by using Wien's displacement law, we can write this. Now we need the ratio of their temperature. Therefore, take this T2 to the denominator and lambda m1 to the denominator. So T1 by T2 is equal to lambda m2 by lambda m1, and their values, the wavelengths, the values of wavelengths are given. So let us substitute that. T1 by T2 is equal to 4.8 into 10 power minus 7 meter divided by 3.6 into 10 power minus 7 meter. 10 power minus 7, 10 power minus 7 gets cancelled. 4.8 by 3.6. So if you take this ratio, the ratio will be 4 by 3. Therefore, the ratio of T1 to T2 is equal to 4 by 3. Well, this completes the problem session of this chapter. So these problems are very important for you from your examination point of view, and you can learn this, and if you carry any doubts, you can contact us. Thank you.